Welcome back, everyone. And so let's continue. So today, we're going to talk about the micro-macro connection. So we talked about the temperature and the pressure, but we never talked about what's happening at the molecular or the particle level of the molecules, what they're doing inside the container. And so the molecules in this room, they're moving around. At what speed are they moving around? Are they moving at the same speed, all of them? Are they moving at different speeds? If they are moving at different speeds, what's the most probable speed? What's the average speed? Maybe what's the average what's the average of the square of the speed? Called root mean square. So that's what we want to figure out. It turns out there is a function that describes the distribution that I'm going to show the function in here just for completeness, but where we actually do the hard work with that function and explore it will be during the worksheet and problem solving section. So I'm going to just write it down. So the velocity distribution is this. We look like this. So these are the speeds. And this is the velocity distribution function called f of t. Again, we'll explore this during the for the worksheet, which is worksheet number 4, basically. And this function turns out it looks like. Let me write down the function, and then we'll draw the shape of the function. It says f of v is equal to 4 pi times n. N is the total number of particles times little m, which is the mass per particle, divided by 2 pi, kb, Boltzmann's constant, okay, kb. Capital T is the temperature in Kelvin, to the 3/2 power times V squared times e to the minus mv squared over 2 kb times t. That's the function that describes the distribution of the velocities. And it looks like this. If you graph it, let's see if you think about it. If v is 0, what do you get if you plug in 0 for velocity? Yeah, you'll get 0, because there is 0, e to the 0 is 1, and these are constants. So it looks like this. And then you can graph it, and it looks, it will grow, peak, and then it will go like this. It's not symmetric, but it looks like this. This one is called the Maxwell-Boltzmann distribution of velocities. We're going to, again, explore this in worksheet 4. So with the velocities, it will tell you how you can find the average or the average squared or the most probable speed and so on. So not all the molecules are moving at the same speed. That's basically what I want to say. Okay. So not all the molecules are moving at the same speed. So now, so I will leave this alone for now, and then we'll come back to it for a little worksheet. What's happening microscopically? What's happening with the molecules? How is the motion of molecules giving rise to pressure? So in a container. So what we're going to do is we're going to consider the simplest way. We're going to take the simplest approach, and it will give us the correct solution or the correct description. So the simplest solution is this. So consider molecules in a box. And so suppose this room is a box. It's a perfect cube. It's not a cube, but let's say it's a cube. It's L by L by L on each side. So the volume of this room would be what? What would you say the volume of the room? L cubed, right? Yeah. If it's L by L by L, it's L. So here is the box. And it's L this way, and it's L deep, right? So the depth is also L. And let's say there are n molecules in this box. Okay? There are n molecules in this box. There are n of them. Okay? And we're going to neglect gravity. We're not going to worry about the gravitational force pulling the molecules down. So the molecules in this room, they're moving in what direction? All directions. Good. Good. So let's say if we have n of them, how many of them, if I ask you, if you have n molecules in the room, how many of them will be moving left, right, versus front, back, and up, down? Yeah, I would say 1/3. There is no reason molecules would prefer to go left, right, versus front, back, or up, down. Okay. So about 1/3 of them, on average, are moving left and right, front and back, and 1/3 will be moving up and down. Yes.
Gravity affecting it?
We're ignoring it.
Would
Neglect the gravity. Yeah, we're going to completely ignore the gravitational effects. Yeah. Yeah, what did we say? 1/3 will be moving in each direction. So we're going to go back to Newton's laws and then think about what's happening. So here is a molecule. It has mass m, and it's moving at speed v. Oh, another thing. All collisions are going to be elastic. Okay, they're going to be elastic. So no loss of energy, no kinetic energy. So it's going to collide. And what happens after it collides with the wall of the container? So it switches and then it bounces back. And since it's elastic, it's going to be v, right? The container doesn't move. Okay. So what's the change in momentum? Change in momentum. So momentum has the symbol P. So P, what I'm going to write here, P for now is going to mean momentum, right? It's going to be what? MV minus what? I want the change. And then MV the other way, right? Now, let's say this one is positive MV and this one is negative MV. So you have MV minus MV, which turns out to be what? 2MV. So the change in momentum is 2MV. Now, okay, good. So if you remember, by Newton's second law, it says the force is the change in momentum over time. Right? Change in momentum over the time is the force. And so this is the force, since it's the force due to one particle, I'm going to name it F1. Because it's the force due to just a single particle. And we're going to start with one particle and then we're going to multiply it by the number of particles that are moving in that direction. Now, this mass, this particle hit the wall. When does it come back? What does it have to do to come back? So it just hit the wall and then bounced. And then what does it do? It has to go here, hit this wall, and then come back. So it has to travel how far in order to come back?
2L.
2L. It travels 2L at the speed v. So the time it takes for it to hit the wall again, the time between collisions, is speed is distance over time, so time is distance over speed. So the distance is 2L and the speed is v. That's the time it takes. That's how much time you have to wait before another collision happens. And so this is m v squared divided by L. That's the force from one particular molecule. Okay. From one particular molecule. Now, if I want, do all molecules move at that particular speed? No. So if I average them, there would be some average speed. But I'm averaging, if I average, I want the average force per molecule, the average force per molecule. These two brackets mean average force per molecule. Equal to this average. The mass is constant and the length is constant, so they have nothing to do. They come out from the average. So this is the average square. So it says this. So you're squaring the speeds and then averaging them. You're averaging the square, and it's called the root mean square. So we will do an example explicitly how to do this root mean square. So I will just name it. It will be called VRMS square, root mean square. So that's the force due to just one of these molecules. Okay? So the total force due to the number of molecules that will hit this wall within that time frame, how many of them will hit the wall within this delta T? 1/3 of the total, right? 1/3 of them, so n over 3. So it's going to be n over 3 times the force per molecule, or the average. So it's going to be n over 3 m over L times the RMS square. So that's the force. Not quite interested in, oh yeah. Yeah, so you would want the RMS, yeah. Because you cannot, they're all, you have 10 to the 23 of them moving at basically different speeds, so we need some kind of an average. So that's the force. So what's the pressure on the wall? Right? Eventually I want the pressure. So what's the pressure? So that's the force on let's say this wall. And whatever happens to this wall, it's the same to the other wall and that wall at the bottom, right? All of them. So what's the pressure on this wall? Force times area or force divided by area? Force per area, yeah. So the pressure, so now this P is pressure. That P was momentum. This is pressure. Pressure, just one up. Force divided by the area. What's the area? L squared. Yeah, the area of, that's why it shows a cube, it's simple. It's L squared. So you would have, the force is N over 3 M V RMS squared divided by L squared. But I have an L at the bottom, so what does it become?
Volume.
L cubed. What's L cubed?
Volume.
That's the volume. Yeah, that's the volume. That's the volume. So you have this. N over 3 M V RMS squared divided by capital V, where V is the volume. Multiply both sides by the volume. We get PV. That's the volume. N over 3 M V RMS squared. Now what's PV according to the ideal gas law? nRT. So it's going to be nRT or NKB times T, right? The reason I chose this form because I see capital right here, that's capital right there. So I want to have them look alike. Okay, so we're going to continue with this one. The next word. So I'm going to multiply both sides by 3 and then divide by 2. So I have this. I'm going to multiply both sides by 3 and then divide by 2. So when I do that, I will n times 1/2 m v RMS squared is equal to, I multiply by 3 on the right side and then divide by 2, and times p. Okay? So, what does this part represent? 1/2 mv RMS.
Kinetic energy.
Yeah, that's the average kinetic energy per molecule, right? Yeah, that's the average kinetic energy per molecule. What happens when I multiply the number of molecules by the kinetic energy per molecule. What do I get? The total kinetic energy for all the molecules. And that's known as the thermal energy. So let me write here. So usually people write this as small epsilon like this. And this one is capital N. This is the energy per molecule. This is the energy per molecule. Energy per molecule is small e, or epsilon, is 1/2 m Vrms squared. And that's equal to N times 3/2 kb times T. So I think you all just said the number of molecules, the total number of molecules times the energy per molecule is the total energy, right? Is the total energy. So this is just the total energy, which we call thermal energy. Thermal. That's the thermal energy. And I have here, and times 3/2 kb times T. I'll come back to this in a second. So here's the conclusion. I will come back to this. The conclusion is this: 1/2 Vrms, 1/2 m Vrms squared is equal to 3/2 kb times T. So the kinetic energy is related to the temperature. The kinetic energy of the individual molecules is related to the temperature. If the temperature is higher, what do you conclude about the kinetic energy?
Higher.
Higher. If the temperature is lower, the kinetic energy will be lower. And if the temperature approaches 0, what does the kinetic energy approach?
Zero.
It also approaches 0. So the higher temperature is a reflection of what's happening microscopically. This is what this group is telling you. So the molecules are moving fast, that gets reflected as up. Yeah.
So, can you describe the velocity so that it would matter the sign whether it's going in X, Y, and Z? And how come you multiplied it by 1/3 of n if you're splitting it up into like, because you're using a special definition energy theory, right, to split it up into the three.
I did not mention that yet.
Can you explain why you didn't divide it by 3 then?
Oh, I said, let's just take a very simple model. We have a total of n molecules. Let's assume 1/3 of them are moving in each direction.
Oh, so
Approximate.
then everything else was just calculated from X direction
Yeah.
instead of Y?
Yes, yeah. So I just said, assume you just have 1/3 of them just consistently moving in the X direction,
does,
a third moving in the Y direction, and a third moving in the Z direction. And that's very reasonable, because on average, they have no preference to go in the X or the Y or the Z. So about a third of them.
And their speed in each of those 3 directions would be about the same.
Yes, yes, yeah.
So since their velocity is about the
Oh,
same,
rata.
then wouldn't their velocity RMS also be about the same direction?
Yes, yes.
So then how come we don't times the average energy the average force per molecule? Why don't we times that by the same? Why do we times it by X?
Gusto tayo ulit.
No, because, so how many molecules are hitting this one?
Just the ones in the.
Yeah, just the one, so a third of it.
But since all 3 directions are going at the same speed, when you calculated the velocity that can count for all 3, I don't get why we're doing one of it.
Let me see. So one molecule, this is fine, right?
Yeah,
For the molecule. The average per molecule, that's fine, right?
yeah.
Now, the total force, let's say if I want the total force on this wall, I need to multiply the force of one molecule by the total number of molecules that hit this wall within that time, right? Right? And how many molecules are going to hit the wall by the time one of them goes back and forth?
Okay, the force per wall, it's not like the force of all the walls.
No, just we're focusing on one wall. And whatever happens on that one wall would be the same on the other, say, 5 walls.
Okay, that makes
Good. Okay. solve for VRMS. So VRMS here is going to be, and we will do a few problems with numbers so we get a feel of what this means. So VRMS is going to be multiplied by M. So 3 kV temperature divided by mass. So, and by the way, up to this point, we're assuming our gas is just monatomic, right? It's one particle. We will talk about if it's diatomic in a little bit. So, first, I want to discuss this average thing, RMS. So let's consider, suppose I have five particles. Here's the first example. It's going to be simple. Consider 5 particles. 5 particles of speeds in meters per second. One of them has 500, the other one is 600, 700, 800, and 900. So 5 particles have these speeds. Obviously this room has 10 to the 25 or 10 to the 20 something. Much larger than this. So let's find the average speed. What's the average speed? The average. How would you find the average speed?
Add the model and divide by 5.
Yep. So it would be 500 plus 600 plus 700 plus 800 plus 900 divided by 5. And that turns out to be 700. Yes? 700. Now VRMS, on the other hand, here's how you would find VRMS. VRMS, you would square them first. Average that square, and then take the square root. In other words, you would do this. Take the 500, you square it. And then the 600, square it. 700, square it. Square this one, square 900. Add them all together. Divide by 5. After you have done that, now we take the square root. Square root includes includes everything. And it would be 700. And 40. Yeah, everything. So, with that, let's do another example. Just want to find out what is the speed of gas molecules at a certain temperature. Okay. So suppose I have a container with helium gas. Here's an example. Here's a container. There is helium. Pressure is 200 kilopascals. Temperature is 60 degrees Celsius. And helium is, what's the mass of one helium particle? Look at the periodic table there. So it would be, the atomic mass number is 4, right? Yeah, 4 times 1.66 times 10 to the minus 47. So it's approximately, so 4 times 1.66 times 10 to the minus 47. That is 6.64 times 10 to the minus 47 kilograms. So each of them has this much. So the question is, what's VRMS? How do we do this? What do you think?
Use the formula.
Which one?
No,
This one?
right
Yeah.
there.
So do we need the pressure?
No.
No. So the pressure is just extra information that you don't need. So don't, if you don't need the information, then you don't need it. I remember in one of the quizzes I gave before, it was about calorimetry. I gave like the latent heat of fusion, the vaporization, and it never got to the vaporization point, but people felt obligated to somehow use that number. You don't have to use every number that's given, right? You just have to decide. And I purposely put it because you have to decide what number. You can get the handbook of chemistry or whatever it's called with a bunch of things that you don't need. You have to decide. Yeah.
Is the T in that equation Kelvin or does it not matter?
So PV equals to NKVT, so it has to be.
Oh, yeah.
Yeah. So, yes, so here it is. V RMS is V KV times T divided by the mass square root. So you have 3 Boltzmann's constant is what? 1.38, right?
Yeah.
1.381.
Times 10 to the 20.
Minus 23 joules per Kelvin, right?
Yeah.
I'm going to plug in the units on purpose. And the temperature is 60, but we have to add 273, so 323 Kelvin. Divided by the mass is
30.
of 30. Like this? Times 10 to the minus 27 kilograms. And you have to square root of all this stuff. Notice Kelvin go away, and now you have joules per kilogram. This is RMS speed, so it needs to be meters per second. So it's a joule per kilogram, and we square root it, you get meters per second. The answer is yes.
Yes.
But how? Well, a joule is a Newton times a meter. Joule is Newton times force times distance, right? Newton times meter divided by kilogram. And Newton divided by a kilogram, force over mass is acceleration. So meters per second squared times meters. So that's meters squared per second squared square root of meters per second. So yeah, the units will work. And what do we get? This one's 1440. Okay. Let's see if you can estimate without doing any calculation. Okay? Let's see if you can estimate without doing any calculation. So I'm not looking for an exact number. I'm looking just a ballpark. So helium, these are helium. Then we move it at 1440, right? At this 60 Kelvin. 60 degrees Celsius, 333 Kelvin. What if you have O2 molecules? O2 would be diatomic. Let's treat it just like helium, monatomic. Assume this formula works exactly like it. What changes? The mass. So O2s have how much in comparison to the mass of helium? It's how many times the mass of a helium?
8.
8 times, right?
8 times.
Yeah, 8. Because it's O2, so 32. Yeah, so it's 8 times. So what do you think the RMS is going to be, approximately?
Times by 2 square root 2.
Square root of 8 will be divided by about the square root of 8. What's the square root of 8? It's about 3. Yeah, we're doing approximation. So it would be about 500. It would be about 500.
5,000.
Huh? It would be about 500 meters per second.
Oh yeah.
One more of these. Talk about other things. So, you know what STP is? STP, standard temperature and pressure.
Yeah.
temperature peak, it's STP. It's 273. How about the pressure?
One atmosphere.
Yeah, that's what STP means. So, what would be the total kinetic energy of 1 mole of helium? 1 mole of ideal gas in this situation. What is my in total translational kinetic energy of 1 mole of gas at STP? So suppose you have 1 mole of gas at this temperature. What's the total translational kinetic energy?
I times O.
So translation kinetic energy is 1/2 mv squared.
Yeah.
That's the translation kinetic energy.
And then rotation.
So how do I
Absolutely.
find it?
Square. Translation words.
If you have one of them, what's the kinetic energy for one? Which one? Yeah, 1/2 mv squared. The problem is I don't have the mass and I don't have v. So, yeah. So the energy per particle, one particle will have this much energy. Okay. That's how much. If I want all of them, total energy, it's going to be the total number of particles times this. So this is going to be 3 halves times n times kb times t. Now what's the number of particles? Huh? Avogadro's number. It's 1 mole, so it's Avogadro's number. But we like to work less hard, so we can just transform. Because we're given the number of moles, we can rewrite this as 3 halves n RT, right? And n is 1. So that's calculation. So I have 3 halves. N is 1 mole. And R is SI units, 8.314. 8.314. And then T is 273. We get E. 3,400 joules. Approximately. 3,400. That's the total energy. Total translation. Yeah.
So the total translational is the E thermal, the energy.
For monatomic, yes. Yes.
Or for
Because there is no
monatomic.
rotation. So let's stick with that for now. Right? No rotation.
Okay.
At the moment. Yeah. So that's why I just said translation. It's not the motion in the X, Y, and Z. So I should have asked what's the energy per particle. Let's do that. Energy per particle is going to be just 3 halves kBt, right? It's going to be 3 halves kB times 3. Let's see what that is. So it's 3 halves. kB is 1.381 joules per Kelvin. Times 10 to the minus 43 times 273. Yeah, it should be small, right? The energy of one particle should be small, very tiny. Turns out to be 5.65.
divided, our first answer 3,400 by the
Yeah.
total number.
Yes, by Avogadro's number. Yeah, correct. It's just a matter of convenience.
Right.
Yeah. The ideal gas law, PD equal to nRT or NKPT. It's just a matter of convenience whether you use capital N, number of particles times moles constant, or number of moles times the ideal gas constant. It just depends, but they're the same. So now, let me go back to this thermal energy.
The PV, that PV sama dengan kan N kecil, sama juga PV sama dengan N besar kali.
So the thermal energy, I'm going to talk. We assumed it's monatomic. The thermal energy is
Bukannya N di
3 halves and KP times T, right?
So PV is
Yes, are you with me? Just copy that. Now, again, as a matter of convenience, I'm going to write this as 3 halves N RT. 3 halves N. And this is N times 3 halves R times T. And what's 3 halves times R? You have seen that number before.
CV.
Yeah, that's CV. So it's N times CV times T. N CV times T. And this is CV for monatomic, right? CV for monatomic. And so that means the change in thermal energy, this one we have seen before. It would be N doesn't change and CV doesn't change, assuming you have the same number of molecules. It's going to be N CV times delta T. Remember this one? We said it works for any process. It doesn't have to be just isomorphic. So that's one. So this is for monatomic. Now I want to discuss, before I discuss diatomic, motivate at least what's going on. I would like to look at this one. So any questions on how we got here? I think this is it, right? Okay. So let's look at the energy per molecule. The energy per molecule for monatomic. We said it's 3 halves